All right, let's dive in. Integration by parts. So last time we did substitution. Sometimes you'll hear me a lot of times you refer to it as U sub or U substitution. And a lot of the ones we looked at on Thursday had some kind of multiplicative structure in the integrand. Integration by parts also typically has a multiplicative structure in the integrand, and we can't use U sub. So as we start to build more techniques of integration, one thing I want you to be very conscious of is why you're using the technique you're using, okay? The reason I want you to be aware of that, a couple reasons. Number one is good for practice. It'll help you get the technique down. Number two, eventually, when we're done with this module, you're going to get a bunch of integrals, say, on the module quiz, and it's not going to tell you which technique to use. So you're going to have to think about which technique to use. So we always start with the basic antiderivative. Do we have a basic integral? If we don't, then the next thing we want to look for is a possible U substitution to find the antiderivative. That's what we worked on Thursday. This very first example I'm going to do here, x e to the x dx, is a perfect example of how we'd walk through this. Well, because of the x here, or because of the e to the x, whoever you want to blame in this case, this is not a basic antiderivative. If it was just the integral of x dx, it'd be basic. If it was just the integral of e to the x dx, it'd be basic. But it's not. It's got a multiplicative structure in there. So the next thing we think about is U sub. Well, U sub's not going to really help us, you know. Let's just say, for argument's sake, sorry about that. I want to do this. Let's just say, for argument's sake, we did want to try U sub, which is nothing wrong with that, guys. There's nothing wrong with trying U sub. Well, we know a lot of times we let, you know, U be x and then du is dx. Well, the du is a very easy sub in, and so is the u. But if we were to sub those in, we get u e to the u du, which is really exactly where we started, just a different variable. So U sub is not going to be not going to help us here. So we go to the next one that works really well on multiplicative structures, which is our integration by parts. This is the one you learned in the lesson. Integration by parts is interesting. You know, if you take it, it's in the lesson, so I won't go over it in class, but basically what's happening is it's derived using the product, which is why it works well on a product. Now, with integration by parts, we use the entire integral. We're going to let one piece of it be u and one piece of it be dv. These are the guys we get to choose. After we choose those, we're going to calculate du, which I'll put here, and v. Now, because we get to choose these, and then we have to calculate du and v, ideally, we want things to get easier with those calculations. Here's what I mean by that. My u is going to be x. All right, well, if that's u, then that leaves e to the x dx for my dv. Now, this is actually very similar to doing u substitution. Once we have our du is just the derivative of this, which is 1 dx. And you don't really need to write the 1. In fact, most of the time I won't. I just wanted to put it in there for this first example's sake. All right. Well, this is easier than what we started with. That's what I meant by get easier. We want to choose u and dv so they get easier, or try to choose them so that they don't get harder. That's not a hard and fast rule. Sometimes we can't help it. Sometimes it does have to get a little bit tougher, and I'll show you one later where that's the case. All right. So our dv, well, what this is v is the antiderivative of dv. So we need the antiderivative of e to the x dx. Remember, this is our favorite in calculus. E to the x is our favorite because its antiderivative is the same as the function. So, okay, it didn't get any easier, but it also didn't get any harder. So that's always kind of your first rule of thumb when choosing your u and your dv. You want, when you calculate du and v, for them to not get harder. Again, that's not always going to be the case, and I'll show you an opposite case a little bit later. Okay, now this next part, guys, you're just going to want to know it. uv minus the integral of v du. That's how we put integration by parts back together. By the time you're done with the 5.4 homework, you will have this down. But what I would say is while you're doing the homework, have this on a little note card, refer to it while you're going through problems. Once you've done 10 integration by parts problems, you will have this down. Because the last thing you want to do is get this part correct and then have a mistake putting it back together, because that'll mess up your final answer. But we just follow this pattern. So uv, so x e to the x minus the integral of v du, e to the x dx. Now here's something I want to point out. Notice there's no integral symbol in front of the x e to the x. It's done. This is part of our final answer. We don't need to do anything else with this. If there's constants, we might simplify them if need be, but we don't need to do any more integrating or derivation with this. This is done. Now we focus on this integral. Ideally, after a round of integration by parts, we get to something basic or maybe something that requires a u sub. But we might not always. We're going to see sometimes this integral may require integration by parts. Okay. This is a basic antiderivative. We actually just did it right here. And we get x e to the x minus the antiderivative, which is e to the x. I have an indefinite integral, so what do I need for this answer to be 100% correct?
Plus c.
Plus c. All right. It's an indefinite integral. We need the plus c. Good job, guys. And there is our general antiderivative for this problem. Questions about this one? Okay, let's do another one. This one we'll do as a definite integral because there's just a couple things I want to mention. But realize with the definite integral, really, what do you need? You need the antiderivative, which is what we just found in the previous problem. And then you do the upper limit of your antiderivative evaluated at your upper limit minus your antiderivative evaluated at your lower limit. Okay, so you can do the integration by parts, get your antiderivative, and do your limits. But I just want to point a couple things out. This one is very similar to the last one. A u sub still won't work because of the same issue as before. We need this to, we would need, if this were x squared and this were x, u sub would be great. It's not. So integration by parts is a good candidate, and we're going to have this very similar setup to the last one. So u equals x squared, dv equals e to the x dx. And this is something you guys are going to notice as you do more of these. If you've got a polynomial times what's called a transcendental function. Transcendental functions are e to the x and are trig functions. If you've got a polynomial times a transcendental, it's basically going to be u is your polynomial, your dv is your transcendental, and you do it however many times until you get to a basic antiderivative. So now 2u du, excuse me, is 2x dx. V is e to the x, just like last time. Put this together the same way. uv, so, oh my goodness, I forgot an x. Apologies. X squared e to the x minus the integral of 2x dx. 2x dx, excuse me, e to the x times 2x dx. E to the x times 2x dx. All right, now we're gonna clean this up a little bit. One thing I want to make sure we're all on the same page on, this is a definite integral, okay? So the limits are still 0 to 1. Notice the variable never changed. So unlike u sub, where we actually changed the variable, this stayed as x, the limits stay the same. Like I told you before, this is already out of the antiderivative. So we can actually put the line behind and put 0 to 1. If we want, we can put the limits in now. And so we're going to do that. It's up, this is user preference. If you'd rather do the whole antiderivative, then incorporate the limits, that's totally fine, but you can also do the limits as you go. Because one thing I can't stress enough about integration by parts is to keep track of what I call bookkeeping. What I mean by that is keep track of your negatives, positives, and your coefficients. Because if you need to use integration by parts 2 times, which we're going to in this problem, 3 times, guys, you can get a problem where you use integration by parts 5 times. You really need to keep track, especially of this negative right here. So you take your time and you write everything out nice and neat so that you don't have a sign error somewhere. Okay, at this point, I can incorporate my limits. So let's see, we would have 1 squared e to the 1 minus 0 squared e to the 0. This is done. Whatever number this comes out to be is going to be part of our final answer. This we still need to work on. I'm going to do a little bit of rearrangement. I like to pull any constants out front. So I get minus 2 times the integral from 0 to 1 x e to the x dx. Okay. Now we'll clean this up. 1 squared is 1, e to the 1 is e. This whole thing just goes to 0. So this all just comes out to be minus 2 times the integral from 0 to 1 x e to the x dx. This integrand should look really familiar. So I'm not going to read, actually we will redo it. So I just want you to see what integration by parts looks like twice. But we actually just did this one. We already know the antiderivative. Not a problem. I think it's worth doing again, just because I want you to see, we can do, guys, we can do integration by parts over and over. Let's do it in a different color just to make it real obvious. If need be. Integration by parts can be basically an iterative process. So u is x, dv is e to the x dx. Like we saw last time, du equals dx and v equals e to the x. Now here's where bookkeeping comes in. Let's throw some equals on those. So we have e minus 2. I like using brackets just to kind of remind myself this minus 2 is going to apply to what I'm doing in here. Okay. So I've got uv, which will be x e to the x minus the integral of v du e to the x dx. Close that bracket. This is a definite integral from 0 to 1. Oops, let's put the line in there first. From 0 to 1. Now again, we can do this part now. This we got a basic antiderivative. But we really need to be careful with our bookkeeping. So minus 2, I'm going to keep my brackets. Plugging in 1, I get 1 times e to the 1. 1 times e to the 1. That look a little more like an e. Minus 0 times e to the 0. Okay, that's doing our fundamental theorem on this part here. Minus, we know the antiderivative of e to the x is e to the x from 0 to 1. So I still have to incorporate my limits one more time. Those brackets, remember, eventually I'm going to distribute this minus 2. Let's get everything done here. So e minus 2. 1 times e to the first is just e. 0 times anything is 0. Minus, now I'm going to plug in these limits. E to the 1 minus e to the 0. And I hope you guys can see how important these parentheses are because of this minus. It's why the bookkeeping is so important on integration by parts. Because of this minus in the formula, we're constantly having to distribute that negative. So let's do it from the inside out so we don't miss a step. First thing I'm going to do, this, I'm going to distribute this minus. So I have e minus e. E to the 0 is 1. But notice it's a negative and a negative 1, so it becomes plus 1. E minus e, those cancel out to 0. So I end up with negative 2 times 1. And our final answer is e minus 2. Again, I want to stress the reason I was doing this one, I wanted you to see one where we have to do integration by parts twice. What tells me this is going to be an integration by parts twice? Well, I'm not getting rid of the e to the x, but I know every time I do a round of integration by parts, this power here, the 2, is going to become 1 less. So I can say, hey, if I do integration by parts twice, it's eventually going to get rid of this piece here, and I'll get my basic anti-derivative. The other reason I wanted to do this was as a definite integral to show you how you can take the limits and incorporate those as you go. If you didn't like that, that's okay. Don't put in the limits. Just get your antiderivative and then put in your limits at the end. All right. Questions about that? About definite integral with integration by parts, but having to do integration by parts multiple times. All right. Next one. This one's kind of a cool one, and I want you to see it. You'll get one like this in the homework because there's something interesting that goes on with this one. Now, in the last two, we had a polynomial times a transcendental. This case, we have 2 transcendentals. All right, so nothing's getting easier and nothing's getting harder. We're going to let u equal, let's say, e to the x. We're going to let dv equal cosine of x dx. All right, just arbitrarily pick those because the derivative or antiderivative, this is still e to the x. The derivative or antiderivative, this is sine or negative sine depending on which value. So we get a du, which is e to the x dx. And over here we get a v. Now careful on this. I know it's can be hard to remember which direction you're going. The derivative of cosine is negative sine. The antiderivative of cosine is positive sine. Okay? And if you're not sure, just take the derivative. Oh, derivative of sine is cosine. All right, we start to put this back together. I'm going to do something a little different here because there's some, I know where this is heading. All right, I get e to the x uv, so e to the x. Whoops, sorry, that got a little messy there. Apologies. I'm still not the best online whiteboard writer, even after all this practice. E to the x sine x minus the integral of vd sine x e to the x dx. So I'm just going to write it in this order. Sine x dx. All right. Okay. Now we've got this out of the antiderivative. This, we still have e to the x times a trig function. All right. So I'm going to do something here because I know how the result's going to come out, and I want to show you something. So let's say we get to here and we say, well, that didn't really get us anywhere. Let's try flipping. So this time I'm going to let u equal sine x. And I'm going to let dv be the exponential, e to the x dx. So then v equals e to the x, du equals cosine x dx. Nothing crazy there. All right, now we go to put this together. So e to the x, remember this part's already done, minus, now we got to do our bookkeeping. What's going in the brackets? This is this guy, uv. So I have e to the x sine x minus the integral of v du, e to the x cosine x dx. All right, let's distribute that negative and see what happens. I have e to the x sine x minus e to the x sine x, and distribute that negative here. I get a positive e to the x, integral of e to the x cosine x dx. Now, this is kind of interesting. These cancel. And we get the integral of e to the x cosine x dx. Well, remember where we started. We started here, right? So we bring that down. We get integral of e to the x cosine x dx. So what did we find out? The integral of e to the x cosine x dx is equal to the integral of e to the x cosine x dx. It's not wrong. I mean, that's a true statement, right? It just doesn't get us anywhere. We found out that the original thing we asked is equal to the original thing we started. Yeah, we basically went in a circle, right? Okay. Not to worry. We're going to go back to blue. I'm going to redo that part, but I'm going to do it a little differently. All right, so we're going to go back to blue. We're going to go back to this part. E to the sine x minus integral of e to the x. I mean, guys, we did nothing wrong. We did nothing mathematically wrong, and we got a mathematically true statement, okay? It just doesn't answer our question. So here's what we have to do. Instead of switching, let's keep them the same. So u equals e to the x, just like we did u last time, and that's going to leave for dv sine x dx, okay? Then our du, we already know this one, it's e to the x dx. Our v, well, the antiderivative of sine is negative cosine. Turns out the introduction of that negative sign helps us out quite a bit. Okay. Let's put this back together. And with our integration by parts. The e to the x sine x we know is already done, minus. I'm going to get this. There we go. We're bracketing this part. That doesn't look good either. Sorry, guys. Didn't really leave myself enough room to plus that minus. There we go. I just want you, when you go back to look at this, to see how things correspond. Okay, now this is for the integration part by parts here. Now this is a negative e to the x cosine x. That's the uv minus the integral of v du. So negative cosine x e to the x dx. All right. Now let's do something with this, with these. Well, but first off, we got to deal with this thing here. Like I said, I like pulling constants out front. We have a negative, negative. That's going to make a positive. All right. So now we're going to distribute this negative here for our next line. So we have e to the x sine x plus e to the x cosine x. Now, when I distribute that negative to here, it's going to turn it actually back into a negative minus, I'm going to write this in the opposite order. I'm going to bring the e to the x out front. It's multiplication, so we can change the order. Now, this is going to be more useful to us because, again, look at where we started. The integral of e to the x cosine x dx. What we're going to do is we're going to take this guy and we're going to add it to both sides. We're basically going to move it to the other side. It's a really cool little trick that's not obvious if you've never seen it before. This is why we're doing this one. Because what that does over here, that gives us two of them. 2 times the integral of e to the x cosine x dx equals e to the x sine x plus e to the x cosine x. Now, notice there's no integral sign left over here. We have something we can solve. I'm going to multiply both sides by a 1/2. Those cancel. And now I've got my answer. Put on a plus c because it's an indefinite integral. But we have actually solved for the antiderivative of e to the x cosine x dx. So this one, again, this is not an obvious move if you've never seen it before, which is why we were doing this one together. And it worked because I chose e to the x for u both times. It doesn't have to be e to the x both times for it to work. I could have let u be cosine the first time, and then I would have let u be sine the second time. So you either have to pick the exponential and be consistent, or you have to pick the trig function for u both times and be consistent. Okay? You're going to get one like this in the homework, so you're going to get to try this. Now that you've seen it, you know what to do. The trick is to make sure you pick the same thing for you in the first round and the second round, and then look for this common integral to be able to add or subtract over to the other side. It could change depending on if you've got some coefficients in there. It's a pretty cool problem. I think it's kind of a really unique way of thinking about it because we're so used to explicitly solving an integral. Here, we didn't explicitly solve it because we had an integral on the other side, but because those were the same, because this guy here was the same as this guy here, those are like terms. We can add them together, and then all we have to do is get rid of this coefficient over here. Sorry for my messy handwriting. This is x times the arctan of x dx. All right, so we've talked about the choices of u and dv. We like them to get easier whenever possible. So a lot of times we pick x for u because we know that the derivative of it is 1 and it gets rid of the x. This is kind of an interesting, this is where things are not going to be that straightforward. Because here's the issue. If I let u equal x, then I'm letting dv equal arctan of x dx. Well, that means to get v, I need the antiderivative of arctan of x. That is not a trivial antiderivative. And in fact, the antiderivative of arctan of x actually requires integration by parts. So this is not going to be the setup that we want. And so this is going to be a case where, okay, our choice of u and dv doesn't necessarily make things easier. And the reason the way you're going to recognize that is that we know the derivative of arctan. We don't know the derivative of, we don't know the antiderivative of arctan. So when we go to do this, we're going to let u be arctan of x, dv is going to be x dx. Now, of course, when we find b, it actually doesn't get simpler because the antiderivative of x is x squared over 2, but that's okay because we know the derivative of arctan, that's 1 over 1 plus x squared dx. Another example of this, if you had, say, x ln of x dx, same thing. We're not going to have uvx because we don't know the antiderivative of ln of x. It's not one of our trivial ones. And actually, the antiderivative of ln of x is actually found with integration by parts. One of the groups is actually going to do that in homework. So this would be another one where dv would be x dx and u would be ln of x because we know the derivative of ln of x. So ln of x, arctan of x, some of our inverse trig functions, if you get those as part of your product, that's a hint that that's probably going to be your u. And that kind of breaks that rule of thumb of picking x for u to make things easier. So that's why I wanted to show you this one. So uv, x squared over 2 arctan x minus the integral of b du, which is x squared, oops, we have to square over 2 times 1 over 1 plus x squared dx. I'm going to clean this up. This part's done. X squared over 2 arctan of x. I'm going to pull the 1/2 out. So I'm going to have minus 1/2. I like pulling my constants out. And then I've got x squared over 1 plus x squared dx. This is not a u sub. There are some ways u sub could be done with this, but it'd be tough. It's not a u sub. And the reason is because it's an x squared here and an x squared. If this was an x cubed and an x squared or an x squared and an x, u sub would be great. Now, what we'll do, and I'm going to gloss over this for today because it's going to be what we're doing on Thursday. We do something called partial fraction decomposition to rewrite this. So x squared over 2 arctan of x. Don't worry that you don't know what that is right now. It's something we're going to do next time. But basically what we're doing, x squared over 1 plus x squared can be rewritten as 1 minus 1 over 1 plus x squared. And if you want to check it, find a common denominator and subtract the fractions. But because I wanted to show you this one, all right, we can do this integral this antiderivative piece by piece, x squared over 2, arctan of x minus 1/2. Piece by piece, the antiderivative of 1 is x. The antiderivative of 1 over x squared, well, it's right here. Minus arctan of x plus c. And if we want, we can distribute the minus 1/2. So x squared over 2 arctan of x minus 1/2 x plus 1/2 arctan x plus c. I get it. It's not a pretty antiderivative. It's got 3 terms. It's got 2 arctans in it, but it is the antiderivative of this guy. Remember, that's what we're doing in this first module is we're seeing, hey, how many functions can we possibly find the antiderivative by hand? You know, wait till next section 5.5. We get some messy antiderivatives, but we can find those antiderivatives. All right, so again, I wanted to show you this one because this is where we break that rule of thumb of making things easier. But what we would notice is that I know the derivative of arctan, I don't know the antiderivative. So real similar, if we were doing this one, let me just show you what the UV on this guy would look like. We know red is bad, so we'll stay away from this one. But if we were doing this guy right here, just as an example, our u would be ln of x, and our dv would be x dx, okay? And then we would go from there. du is 1 over x dx, v is x squared over 2. And then we just follow the same procedure, okay? I'm not gonna go all the way through that one because one of the groups is gonna get one similar to this. And you're gonna see, I think you see this one in the homework, so you get a chance to try it. But I just wanted to show you an example where it doesn't get easier based off our choices. Questions about that? I'm gonna throw the link to the textbook. And
How did you
Yeah.
figure out that x squared over 1 plus x x squared over 1 plus x squared equals 1 minus 1 over 1 plus x squared? The note, basically. How did you get to that?
Yeah, this part right here.
Yes.
This is done with what's called partial fraction decomposition. We're going to do that on Thursday. So I admittedly completely glossed over that today. So your question is 100% valid. But by Thursday, you're going to know how to do this. It just was needed for this one because this was one of the examples I did.
All right. Sounds good.
But your question is 100% valid. You guys are going to learn how to do this on Thursday, so don't let that be too confusing. We'll say I